All right. Welcome back. Welcome back. Yeah, so let's see. So it's been a little while. We left off talking about incidence Hopf algebras. And if you remember, well, first of all, these incidence Hopf algebras are the Hopf algebras that we built from post-its. And we spent the last few classes talking about many different examples of incidence Hopf algebras. I think we were up to 6 different examples of incidence Hopf algebras. And what I'm going to do today is show you 2 more. I'm going to show you 2 more. And we're going to start to see how this applies to something that might not look like Hopf algebras at all. And so maybe I'll just start out by motivating this with some formulas that are coming from very, very classical analysis. Okay. So let's say that you have some power series, and it doesn't matter too much, but let's assume that the first coefficient is 0 and the second coefficient is 1, and then after that it's whatever it is. Okay, that's some power series, and now let's say that you want to invert the relation. So this is a lot like when you're teaching your students how to find the inverse function. And so what is the inverse function? Well, the way you do it is that you express x in terms of y. So let's say that you do that. And so you get some power series for y. By the way, do you know how to do this? I think this is such classical analysis that probably they don't teach it in analysis classes. But it's a very natural question. How do you find if you have this series of y in terms of x, how do you find the series of x in terms of y? How do you find the series for the inverse function? It's pretty easy to see that it has to start out like this, y plus something. Okay, that'll be a nice exercise for you. It's a nice, simple analysis exercise. It's like a good GRE question, why it starts like this, okay? And then it's something. And the question is, how do you find these coefficients? Okay. And, well, one thing that you could try to do is just do it by brute force. You know, just write x equals like this. The goal is to find, so goal is to find the coefficients of the inverse function in terms of the coefficients of the original function. So what you could do is just plug in. You could just take this thing, x equals this, plug it into here. So you put it into here, x is equal to that. You put it into here, x is equal to that. You put it into here, x is equal to that. And then you get this massive system of equations. And you'll see that that system can be solved. Okay? And it's a little bit, it gets more and more annoying to solve the farther you want to go. So it starts out very easy. For example, capital A is just minus A. Then when you solve for capital B, you find that it's equal to a squared minus b. Then you solve for capital C, and you get 5ab minus c minus 5a cubed. And I really mean it that you can do this. And if you don't see how you would do this, then I encourage you to actually do it. Okay? And get these expressions. d is equal to this. And so on. Okay? And they get uglier and uglier as you go on. But you can keep doing this as far as you want, and if you're very patient, you can do it. Okay. So that's how you find the first few. But then a natural question is whether we can actually do this in general. If I ask you to find the nth coefficient here, can you give me a formula instead of having to solve that system of equations? Okay. So it is a general formula for this. Okay. And that's what I would like to discuss today, and this might spill over to Thursday. We'll see. One thing that I should tell you is that whenever, I've told you this before, whenever a combinatorialist sees something like this, we like integers, and whenever we see an integer, if we see 3, we ask 3 what? 3, what are we counting here? 3 dogs, 3 apples, what are we counting? Okay? And so the agreed answer to a combinatorialist would be that this is the number of ways of doing something. So we'll see what that looks like. So that's a little bit of motivation for the next 2 examples that we're going to see of incidence Hopf algebras. Okay. So we're talking about incidence Hopf algebras. And by the way, if you're still following along, so I told you maybe 3 classes ago that I've been following this paper of William Schmidt. I think it's just called Incidence Hopf Algebras, and I'm still following it. So if you're looking at the paper, this is also there. The trouble with that paper is that he was discovering these things, and very often things are clearer a few years later. So it's not the easiest paper to read, but everything that I'm saying is in there. Okay, so another example is going to be a second Hopf algebra of graphs. Remember what our Hopf algebra of graphs was so far that we studied. So in our first Hopf algebra of graphs, the basis elements are graphs. Multiplication of G and H was just putting them side by side. They don't interact with each other, the disjoint union of G and H. And the co-multiplication was saying, look at the graph and look at any subset of the vertices and do restriction to this subset, tensor restriction to the complement. So it was all the ways of taking a graph apart into some vertex set and then the complement of it. Okay. That was the original Hopf algebra of graphs, and you thought about that a lot, and the homework problem was about that, and you saw Jeremy Martin's talk about that particular Hopf algebra. We're going to talk about a different one today that is similar but is different. Okay. So it'll take us a little while to get there, because I need to introduce a little bit of graph theory first. Okay, so let's say that this is a graph. V is the set of vertices, E is the set of edges, and remember in this class things are finite. Okay, so this graph is finite. And let's take some edge. Okay. And let's actually just do this with a particular example in mind. So Let's say that my graph looks like this. Maybe this will be my graph, and this will be my edge E. Okay. So I'm going to define the operations of deletion and contraction. So the deletion is just what it sounds like. You just delete the edge E. So you just delete edge E. That's all you do. Okay, so here that's very simple. You take the same graph, you just forget about that edge E. Okay? And the contraction it's denoted G/E. And what you're going to do is that you're going to take this edge E and you're going to contract it. Okay, so you're going to contract it into one point and identify the two vertices. So what you do is that you delete all edges. Sorry, I should have said that I'm only going to deal with simple graphs. Okay? And simple means no parallel edges. So you can't have two vertices that are joined by more than one edge, and no loops. So you can't have edges from a vertex to itself. Okay? And so what you do is that you just, let's say that E joins U and V. And so what you're going to do is that you're going to identify vertices U and V. So when you do that, well, let me do it in two steps. So when you identify these two vertices, then what are you going to get? You're going to get this edge is now going to go, first of all, E is going to become a loop, right? And then this edge, and the point is that this is U and this is V. And now they're the same vertex. Okay, this is UV. And so this edge was going to V. Now it's just going here. And then this edge was going from V to this guy. And so now it's going to go from V to that guy. Okay. So that's the first step. I just contract the edge and make U and V be the same vertex. But then because I don't want any parallel edges or loops, I just delete repetitions of edges, and I delete loops. Okay, so remove repetitions, remove loops, and repetitions of edges. So in my first step, I did this, but now I need to remove all loops and repetitions of edges. So I remove this loop. And here I have two parallel edges, so I remove one of them, and I get this graph. Okay, and that's going to be the contraction. Are you guys happy with what this means? So, okay, here's a bunch of easy lemmas about this. Okay, first a really easy one is that if you delete E and then you delete F, you get the same thing as if you first delete f and then you delete e. Okay? It's pretty trivial, right? We agree? A little bit less trivial is that if you contract e and you contract f, you're going to get the same thing as if you contract f and then you contract e. Okay? So contract e, you identify those two vertices. Contract f, you identify those two vertices. And it's almost trivial, except that there might be an issue with removing loops and repetitions, but it all works out. Okay? So it's once you sit down and check it, you'll see that this is pretty easy. And then the other easy lemma to check is that if you delete e and then you contract f, you're going to get the same thing as if you first contract f and then you delete e. And this is a little bit less trivial, but it's also true. Okay? So what that means is that we can talk about, for example, deleting a set. You can delete a set of edges, and you can do it in any order. Or you can contract a set, because you can contract the edges in any order, and it doesn't matter. So if you have a set of edges, we can say that the deletion of that set is just delete the first one, delete the second one, delete the last one, and it doesn't really matter where I put the parentheses because of this lemma. Okay, maybe I'll put this in a little box so we don't get confused here. And if I contract, I can also contract the set by contracting in whatever order I want. It doesn't really matter. Okay? Yep.
I'll have a question. Who came up with the / backslash transition?
So the question is about the notation. Backslash is pretty standard notation for deletion, for like set subtraction, and then because deletion and contraction are always close to each other, and you'll see that both in graph theory and in matrix theory and several contexts, deletion and contraction are always next to each other, and they play dual roles in a way that we will understand. And so if something is called backslash, then the other one probably should be called slash. And so that's the reason.
I think it might have to do with topology. When you quotient out space, you get rid of it in a sense.
Right. I mean, this is a little bit like modding out by that edge. We'll see that this is part of a more general story of deletion and contraction that may be a little bit more familiar, and this is really like modding out.
I was going to ask, does that mean that these graphs are always sitting in a nice space? Were you allowed to do that?
I'm not sure that I understand your question, but one space is the space of graphs. So this is all for E and F different from each other. Okay. And I should also say that if, let's see, let me just budget my board here. You can also write, okay, so a couple more things. So if you have two sets of edges, I mean, think of it as, here's a whole set of all the edges, and then here's T, and then here's S. Okay. So what I can also do is delete. So I want to define this to be what happens when you I want to, in a sense, restrict to the interval from S to T. And the way that I do that is that I delete all the edges outside of T. And so that deletes all of this stuff over here. And I contract all the edges in S. Okay? And so I can just define that. And again, the point is that because deletion and contraction commute, it doesn't really matter what I put first. I could have also written G/S \E minus T, and that would be the same thing. Okay? And you'll see later why we want to make this definition. Okay? Another definition that I want to make is that equivalent to deletion is restriction. So the restriction of G to A is what? Here A is going to be a set of edges. Okay? And so if I restrict to the set A, what I do is that I delete the things that are not in A. Okay? And so restriction and deletion are the same thing. But notice that this restriction is different from the other restriction in the other Hopf algebra, because in that Hopf algebra we were restricting to a set of vertices. Here I'm restricting to a set of edges. And again, you should also notice that here I'm using minus for set subtraction, which is maybe not standard, but if I put a backslash here, it would be pretty confusing. So that's why I do that. Okay. So that's deletion and contraction. And now, what can we say about this? What I want to do next is start with a graph and contract in every possible way. So maybe I'll start with an example, and then we will make some definitions. Okay? And so let's consider all possible contractions of a graph. Okay, maybe we'll do it in an example. We're going to do it for this graph. Okay? I give it some names here. A, B, C, D, E. Okay? I'm going to consider all the possible contractions of this guy. And so let me also I told you that we like to, I'm going to consider the set of all contractions, but I'm also going to put a poset structure on it because we like additional structure when we have it, and it's helpful. So, for example, what can I contract here? There's 5 possible things that I could contract: edge A, edge B, edge C, edge D, or edge E. Okay, and so I'm going to do that. So what happens when I contract A? If I contract A, then these things become each other, and then B and C become the same edge. Okay, and so what I get is this triangle where the edges B and C got identified. Okay? So this is when I contract A. What happens when I contract B? I get a similar picture. Let me just draw the 5 things that I'm going to get.
Question: how do you know which vertex to contract to? You can contract to the one on the left or the one on the right.
So the question is, how do I know? I contracted A.
Okay.
So do I send this vertex over here or this vertex over here?
Yeah.
The point is, remember that graphs are not pictures. Graphs are combinatorial things. And if I had sent it over here, then I would just get the same picture, just looking at a different angle. But it would be the same graph. It would be a different picture of the same graph. So the answer, it doesn't really matter. Okay. So if we contract B, we're going to get this triangle, D, E, A, C. If we contract C, then this squishes the graph and it's going to look like this. is AB, and this is DE. If I contract D, it's going to look like this, CE. And if I contract E, then it's going to look like this. Okay, so now what happens if I take this and let's contract B now? Okay, what happens when so here I contracted A, what happens when I contract B? So here I contracted A, if I contract B, then what happens? This gets squished, the edge C disappears, and I get an edge called DE. Right? What happens if I contract C? The exact same thing happens, right? And so if I contract C, I'm going to get the same picture. So let me not draw it again because I get the exact same graph. Okay. What happens if I contract D? I get something different. Okay. I did this ahead of time, so I'm just going to. So when I contract D, I get what? I get B, C, and E together like this. Okay, and if I contract E, then I'm going to get an edge called BCD. Okay, what happens if I contract A here? I'm going to get just an edge DE, which is this exact guy, right? So if I contract A, I get this guy. What happens if I contract C? I also get this guy. If I contract D, I get the graph ACE. Please correct me if I make a mistake. There's potential for that. If I contract E, I'm going to get ACD. And that's it. Here, if I contract A, I'm going to get, this collapses, and I'm going to get this picture again. If I contract B, I'm also going to get this picture. If I contract D, then I'm going to get AB. If I contract E, I'm also going to get that. Here, if I contract A, I get this guy. If I contract B, I get this guy. If I contract C, I get this guy. If I contract E, I get this guy. If I contract A, I get this guy. If I contract B, this one. If I contract C or D, I get this one. Okay?
Do you need to draw the same edge twice?
I'm sorry?
Yeah, you drew from A, B, C, E to A, B twice.
Oh, no. I'm drawing a poset, and so in a poset you don't put two edges between the same two elements. Thank you. Okay, and so I contracted these in every possible way to get these. Now what happens when I contract anything here? I just get the graph with a vertex and no edges, right? And so I just get this graph. It has no edges. And that's what happens when I contract any of these things. Okay?
And here, then you would like to label labeling?
Here there's nothing to label because we label edges, right? So, and so this is what's called the lattice of contractions of the graph. Okay, you consider all possible contractions, and you order them according to to what contraction went before which other one in the process of contracting. Okay. So you should notice that I'm making a non-trivial claim by calling it this, right? I'm calling it the lattice of contractions, but I defined a poset, and we don't know yet if it's a lattice or not, but I'm claiming that it is a lattice. Okay. And I'm going to explain to you in a second why that is by looking at this from a slightly different point of view. So for example, to get to here, who did I contract? Well, here I contracted A and then B, or I contracted A and then C, or C and then A, B and then A, or C and then A. There's different ways of getting there, but in the end, who did I contract to get here? Well, I contracted edges A, B, and C. Okay, so let's put next to these guys who was contracted. So here, edges A, B, and C were contracted, and I'm going to do that for each one of these guys. Okay, so okay, here's pretty trivial. A was contracted, B was contracted, C, D, and E. Here nobody was contracted. Here who was contracted? It's basically who's missing, right? So here A and D were contracted. Here A and E were contracted. Here B and D were contracted. Here B and E. And here C, D, and E. And what about here? Everybody, right? A, B, C, D. Okay? And so you see that we get some subsets of the edges, but not all subsets of the edges. Okay? For example, what subset is missing? The subset AB is missing. And why is that? Because if you contract A and you contract B, then you also end up contracting C. And why is that in the graph? Because if you identify these two vertices, and if you identify these two vertices, then you have also identified these two, right? Because these guys form a cycle. Okay? And that's a general observation that if you have a cycle, so here's an observation. If you have a cycle in the graph, and if you have an edge of that cycle, then if you take G and you contract all the edges of the cycle except for E, then what can we say about this? Well, if I contracted all the edges except for E, then I identified this vertex with this vertex, this one with this one, this one with this one, etc. And so in the end, I also have identified this one with this one. And so I also contracted the edge E, and so I get this contraction as well. Okay? And so that motivates the following definition. I mean, what I'm after is that I want to describe these red sets. So let me make a definition that a subset of the edges is a flat if whenever C is a cycle, E is an element of that cycle, and C minus E, I say, and F contains C minus E, then F also contains E. Okay? So a flat is going to be a set such that if you contain, so if you contain everybody in a cycle except for that last edge, then you also contain that edge. Okay? And so what I claim is that these red sets that I have here are exactly the cycles. Sorry, are exactly the flats. Okay? So here's my claim. There's a bijection between contractions of the graph and flats of the graph. maybe I won't go through the whole proof, except we can say what the bijection is. What is the bijection? If you take a flat F, then what is the corresponding contraction? Well, it's just G contract F. Okay? And the point is that what I'm doing here is that I'm looking at each contraction, like this contraction right here, and I'm going to say this is several things. This is G contract CD, this is G contract DE, this is G contract CE, and this is G contract CDE. And CDE is the unique maximal set that you could have contracted. Okay, and so it's like for each one of these contractions, you pick a canonical representative, the largest possible representative that you could have contracted. And this gives you a bijection between the contractions and the flats. And so, depending on who you are, you might actually prefer to call this the lattice of flats of G. And actually, I prefer that. So, generally, but I mean, so you'll see both in the literature, lattice of contractions or lattice of flats of G. Okay? All right. So what else should we say now? Well, let's actually explain why this is a lattice. Okay. And the notation for this is, notation that I use is L sub G. This is the lattice of flats of the graph. Mm-hmm.
Because when you do the contractions, they disappear immediately on the first contraction. Or they feel like this is getting more complicated if you start having like larger cycles.
So the question is, what happens if the cycles of your graph are not triangles but something more complicated? Does the picture look more complicated? And I mean, I would say it doesn't look qualitatively more complicated. It's just that if you want a graph that has cycles that are not triangles, and you want it to be interesting, it's going to be a bigger graph. And because it's bigger, it's going to be a bigger lattice. But I wouldn't say that there's a qualitative difference between having triangles as cycles or having larger cycles. At least not off the top of my head. Okay, this is a ranked lattice. So I'm claiming two things. It's ranked and it is a lattice. So let me just sketch a proof. So to check that it's a lattice, I need a join and a meet. Okay. Now, can you see what either the join or the meet is? We know that one particular case where lattices are nice is when either the join or the meet is either union or intersection. So is there any hope of that happening here? That either the join or the meet or both are union or intersection? One thing you'll notice is that join is not union, right? Because the join of A and B is ABC, which is not the union of A and B. But for example, if you take the meet of ABC and CDE, you're going to get C, which is the intersection. And if you look at this picture, you'll see that actually it is true that the meet is just the intersection. How do we prove that? Well, it's an easy thing to check that if F and G are flats, then the intersection is a flat. That's very easy from this definition. Okay. And so if the intersection is a flat, then that must be the meet of f and g. Okay. So our lattice has a meet. Okay. Now, well, we don't know yet that it's a lattice. Our poset has a meet. Now, there is one thing that I wrote on the notes, but I think maybe I didn't say it in class, which is that in a circumstance like this, if you have a meet, then you have a join for free. Did I say this or not? Okay. So if you have a meet and you're finite and you have a top element, then for free you have a join. Let me write this down. If a finite poset with a top element has a meet, then it automatically has a join. What is the join of f and g going to be? It's meant to be the least upper bound, right? And we know how to take meets, which is like taking leasts. And so what you do actually is that you just take the meet of all upper bounds. Okay? You look at all the upper bounds, you take their meet, and that meet exists because this poset does have a meet. This is non-empty because you have a 1, right? And so 1 is greater than f, 1 is greater than g. And so this is a non-empty meet, which means that you can take it. And it's an easy exercise to see that this really is the join. Okay? And this is a very useful lemma that you should always remember when you're trying to prove that something is a lattice. You just, if you can tell that it has a bottom and a top element, then once you have a meet, the join comes for free, or vice versa. Okay? So this is the meet, this is the join. And the join is a little bit more complicated, but it exists. Okay? So this argument shows that I have a lattice. Okay? I want to argue that it's ranked. So what is, so remember, ranked and graded are synonyms. It just means that you have floors. Okay? So what is the rank of a flat? How do you decide what floor you're in? Looking at that picture. How many contractions you made, but you have to be a little bit careful, right? Because, for example, to get to here, did you make 2 contractions or did you make 3 contractions? You made 2, basically. There's an even, it's just the number of vertices, actually. It might be a little bit surprising that it is that simple, but you see this has 4 vertices, this has 3 vertices, this has 2 vertices, and this one has 1 vertex. And it's just the rank is just given by the number of vertices, and I have to get it right because the top. So let's see. I start with the number of vertices. I mean, it's like the opposite of the number of vertices, right? Because if you have more vertices, then you're further down. And so it's like vertices of G minus vertices of F. And I mean, and you have to check that this really is the rank, but it is easy to see that if you perform just 1 contraction, then, I mean, actually, that's the argument. If you perform just 1 contraction, then you collapse 2 vertices. So you lost 1 vertex exactly. So that's the argument that this is the rank. Okay? All right. Cool. So it's a lattice. It's ranked. What do we do with lattices in this class? At least this month. We want to make a Hopf algebra out of this, right? So how do we make a Hopf algebra of this setup? Well, what we do, remember, is we want to. The Hopf algebras that we've been making are the following. You take some family of posets, and presumably these are the posets that we're going to have in mind now. And you're going to define a product and a coproduct. Product is taking the product of the two posets, and coproduct is taking delta of a poset is standing in the middle and going from 0 to x and from x to 1 in all possible ways. Okay. And remember, what do we need for that to make sense? We need the family of posets to be hereditary, meaning that it should be closed under taking intervals. And it should be closed under taking products. Okay. So that should be the next thing that we do. And it's actually going to be pretty easy. So let's make some more observations about this. Okay. Here's my lattice L G. Okay. And so, for example, the coproduct of this lattice would be stand at a vertex of here and then look at the interval from 0 to that and then the interval from that to the top. So let's try to understand what, if I stand at a vertex, what is the interval below it and what is the interval above it. Okay. So let F be a flat so that F is an element of my lattice of flats. Okay, so what is the interval from 0 to F, and what is the interval from F to 1? For example, it's going to be a little bit easier if I look at what is the interval from F to 1. So you look at starting here and then contracting in all possible ways to get to the empty graph. So what is that? It's just the lattice of flats, or the lattice of contractions of this graph. You start with that graph and then you contract in all possible ways. So this is just the lattice of contractions of the graph F, isomorphic. It's not just isomorphic, it's equal. I mean, it's exactly that. Okay, now, what is the interval from 0 to F? You start with this guy, and then you look at all the possible ways of contracting until you get to this one. Okay. So what is that? Well, if you imagine that you take this flat and you contract it, AC and E are all identified, then you'll see that the interval from here to here is exactly the lattice of flats of that contraction. The graph contracted F. And let me write this a little bit differently. It's going to be the same thing, but I'm going to write the graph restricted to F. And so, and more generally, if you have two different flats, let's say F1 and F2 are flats in this picture, F1 is less than F2, then the interval from F1 to F2 is going to be isomorphic to the lattice of the graph restricted to the interval F1, F2, which is that graph that I just wrote earlier a minute ago. Okay. This is something that I think the best way for you to believe me is to look at a big graph and draw it, and you'll see that this is true fairly trivially, but you just have to draw some examples, and I think you'll find it very believable. Yeah.
Originally, for the interval f to the top element is isomorphic to L sub g restricted f. You wrote L restricted f. In that notation, how would you write that for the interval f1 to f2 isomorphic L sub what? Or would you not change that?
So, okay. So Krista's question is, I had written LF, and then I changed it to this.
Yeah, I like the LF, but it's okay. You wrote it as g restricted f because you're talking in terms of our graph tree.
Yeah. And so the question is, how would I write this one in that notation? And I would write it as F2 contract F1. Yeah. So. So I would argue that this is exactly not awkward. And the reason that it's not awkward is that this statement is true. And so this operation, actually I think what seemed awkward was to define this. When I defined this over there, I saw the look in your face, what is he doing? Now you see what I'm doing. And now you see that in retrospect, really I was just putting whatever notation I needed to put so that it matched this. And so the way that you should think about that funny construction that I did over there is not what I wrote, you should think of this. Okay? And I actually think that this is a very good choice of notation for that reason. If slightly, it's not ambiguous because really they end up being the same object. Okay. So, again, these are some very nice facts that if you don't see right away why they're true, then I do really advise that you stare at this for a little bit longer. If you're watching the video, maybe stop the video and do some examples. But what's the point of this? The point is that if you take a lattice of flats of a graph and you take any interval of it, you get the lattice of flats of a graph. And so that means that the family of lattices of flats of graphs is closed under taking intervals, which is a very good thing if we want to make something hereditary out of this. What else do we need to have a hereditary family? We need to be closed under taking products. And that turns out to be pretty easy also. If LF and LG are the lattices of flats of two graphs F and G, then I want to claim that if I take their product, the product of the lattices, this is also the lattice of flats of a graph. So I need to invent a graph that has that lattice of flats. Let's think about what that graph could be. There's not that much that you can do, I'm telling you. Input, a graph F and a graph G. Output, some graph that you put here so that this equation is true. There's not that many graphs that you can invent out of two graphs F and G. So what should we do? Disjoint union seems to be the most natural choice. At least it's the simplest construction out of two graphs, right? Let's think about this. Does this have any hope of being true? For example, one thing that you could ask us is, what are the ranks? What is the rank of a lattice of flats? How many floors does it have? This one has 4 because there's 4 vertices. We talked about how it's just number of vertices, okay? And so this guy has rank number of vertices of F. This guy has rank number of vertices of G. If you take a product, the ranks add. That means that this has rank number of vertices of F plus number of vertices of G. And this is weak, but still some evidence that this might be the right thing. This is very easy. You just, I mean, once you sit down and check it, you'll see that. I mean, what's the bijection again? What's the bijection? An element of here is a flat of. So here you have a graph F and a graph G. An element of this guy is some flat of F. Okay, and so let's call it maybe I don't know, flat sub F. Not the best notation, but okay. An element of here is a flat of F. An element of here is a flat of G. Where should I send this to? A flat of F is some set here that has this property of being closed under cycles. A flat of G is some set here. What should I send it to? I mean, here the picture is, this is my graph, F and G. And so I need to make a set here, and what I do is I just take the union. So I claim that if I have a flat of this side, and a flat of this side, and I take the union of them, then I get a flat of F union G. Okay? This is so trivial that I drew the same picture on both sides. But it's one of these things where you know the book will write trivial and you'll get annoyed, and then you'll do some examples, and then after an hour you'll say, okay, yeah, it was trivial, but it's like an hour's worth of trivial maybe, or not an hour, I mean, but anyway, you know what I mean. Okay, the point is that this is great news because we have a hereditary family in our hands. So that's the conclusion of this, right? The conclusion is that if I consider the family of lattices of flats of finite graphs, finite simple graphs, this is a hereditary family. And so I get a Hopf algebra. Okay. Now, the elements of this Hopf algebra are lattices of flats of graphs. But it's just, I mean, for example, a basis of that algebra is this lattice. But I think it's going to be much easier for us to think that the element is not the lattice, but the graph. Okay, and so instead of writing everything in terms of the lattices, let's write everything in terms of the graphs. Okay, and so let's say let me just go over here. So finite simple graphs. And we're going to make this into a Hopf algebra. By taking the span of those graphs. And we're going to say that the product of two graphs what should the product be? We want the product of the lattices. What we're seeing here is that the product of the lattices corresponds to the union of the graphs. Okay, so I should define the product to be the disjoint union of the two graphs. And you'll notice it's exactly the same product as in the previous Hopf algebra of graphs. The difference is in the coproduct. What is the coproduct of G going to be? The coproduct of G is going to this lattice and summing over the lattice of flats. So I need to sum over all the flats of my graph. And then what do? Given a flat, I go from 0 to the flat and from flat to 1. But again, I don't want to write it in terms of the lattices. I want to write it in terms of graphs. So instead of writing, go from the bottom to F, I write the corresponding graph, which is I think I have something backwards in my notes, but from the bottom to F, I get G mod F, and from F to 1, I get G restricted to F. So from the bottom to F and from F to the top. Okay. And I always want to get lazy and not do this, but then I always end up doing it. So what's the unit? It should be a graph that when you multiply by that graph, you don't change the graph, and so this should be the empty graph. And the co-unit, as usual, is going to be 1 if the graph is trivial and 0 otherwise. Okay. And so, from the general machinery, I mean, before Hopf algebras existed, or were put into this context, graph theorists knew about the lattice of flats, and the point is that if you can encode a graph in terms of its lattice of flats, then because this family of lattices of flats happens to be hereditary, you get a Hopf algebra for free, and this is the Hopf algebra that you get. Okay, so that's my second Hopf algebra of graphs. Is it really a second Hopf algebra, or is it the same one as before? Remember that in the other one, I would sum over vertex sets and then restrict to that vertex set tensor the rest of the graph. Okay? Which means that the number of summons here was 2 to the number of vertices, whereas the number of summons here is the number of flats. And so this is really something different from the other one. Okay? Okay, so now let me say that unfortunately I drew this picture upside down. You'll see in my notes that I have the exact same picture but upside down. And that means that everything is true but upside down. And so that's why I hesitated here, because actually what the standard definition of this is the exact same thing but with these two swapped. And the only reason is that I drew the picture upside down. Okay? So just, imagine that for the last half hour everything was upside down, and if you did that, then you would get that this is restriction and this is contraction. Okay. But by the way, give me just a second, Carla. So, you can always do this. I mean, if you have a Hopf algebra and you have the coproduct defined in some way, then if you just decide to twist the coproduct, that's also going to be the twisted version of that Hopf algebra, and it's also a Hopf algebra. And so, if you believe me that the other one is a Hopf algebra, then you should really believe me very easily that this one is also a Hopf algebra. And this is the one that I wanted to write down. Question?
This is the one that's upside down, not the one in the middle.
Right. So, well, okay. So the problem is this. The problem is that there's a difference of convention, because some people draw the lattice of flats like this. I would say this: the people that think of this as lattice of flats, like me, draw it like this. The people that think of it as the lattice of contractions draw it exactly the opposite. And so I said that they're the same poset, but they're the same poset up to how you draw it. Okay. And so according to what version you do, you get this. You get. I can't say one is. I mean, they're both correct, and depending on what your convention is, you're going to get either this Hopf algebra or the twisted one. Okay. Okay, so this is a Hopf algebra. This is a Hopf algebra. Any questions about this Hopf algebra? Yeah?
Wait, what happened to the general formula?
Yeah, so it's very natural for you to ask, well, what on earth are you doing? I thought you were going to talk about analysis, and so far I haven't said anything about this. We'll get there. We'll get there. So we'll get to what I want to illustrate is that one very nice way of understanding these formulas is in terms of this context of Hopf algebras of graphs. And this is very mysterious at the moment, but by Thursday you'll know what I mean. But I think today you're not going to know what I mean. Okay. But are we happy with this definition of this Hopf algebra? Great question. So I'm claiming it's a Hopf algebra. Do we have an antipode? Remember, there's a cheap way of answering this, which is if you're graded and connected, then you have an antipode for free. Okay. So is this graded? Yeah, right? I mean, these things have floors. And that must mean that it's graded. It is graded. Is it connected? What does it mean to be connected? It means that the things of degree 0 are precisely a copy of the field. Okay? So what graphs have degree 0? Actually, I'm really glad that you asked this question, because precisely the next point I was going to make is related to that. What graphs have degree 0? The empty graph has degree 0. But can you think of other graphs for which there are no contractions? If you have a single vertex, there's nowhere to contract it. Or if you have a bunch of isolated vertices, there's nowhere to contract them, because there's no edges to contract. And so actually here, this Hopf algebra is not connected, because any graph that doesn't have edges has a lattice of flats that is just a point. And so that means that every graph with no edges is degree 0. Okay? So
The degree was the number of vertices. So in that case, then the single point would be degree 1.
the thing is that, okay, so there's something a little bit unfortunate, which is that we're talking about two different notions of degree. Actually, we're not talking about two notions of degree. We're talking about degree versus rank. And so the rank of a bunch of points might be something. But But the degree is the height of the poset, and if you have no edges, then you have no, the poset is just a point. Okay? And so, actually, it's customary because it's more useful to just mod out by that triviality, because the point is that the lattice of flats never sees the isolated vertices, right? I mean, if my graph was like this picture would never see that. You just have these 2 points in all of these guys. Okay? And so it's actually more useful to so a better variant of this is to mod out by isomorphism except for isolated vertices. In other words, what I want to say is that this graph is the same as this graph. Okay? If I mod out by this thing, then it is going to be true that this Hopf algebra is connected, and therefore for free we have an antipode. But that's a cheap answer. That's not the answer you want, Carla. You want a good answer. You want what is the antipode, and I'm glad you asked, and well, the antipode has to do with this. So we have an antipode, but we like to find it, and then when we find it, we'll see what it has to do with this stuff. Okay? Let me make another comment, which is that we can also do another variant, which is to consider not all finite simple graphs, but just a smaller family of them. This also works for any family of graphs well, it doesn't work for any family of graphs. I mean, I could make this definition for a family of graphs, but what does that family of graphs have to satisfy? Well, it should be, I mean, I'm thinking of the span of just some select set of graphs, but it should be that if you take the coproduct of a graph, then this should live in your set, and this should also be in your set. And so what you want is to consider a family of graphs that is closed under this, closed under this, and closed under this. So this also works for any family of graphs closed under deletion, contraction, and disjoint union. Okay. If you have any collection of graphs that satisfies these properties, then we can make the exact same definition, and it's going to make sense. If G and H are in the family, then the disjoint union is in the family. And if G is in the family, then this is in the family, and this is in the family. So the same formulas make sense, and we're also going to get a Hopf algebra. Okay. So this is what's called a hereditary family of graphs. Okay. And so I hope this starts to get your wheels turning. What families of graphs can you think of that are hereditary? For any such family, you're going to get a Hopf algebra, and then hopefully if we pick the right family, then the Hopf algebra is going to be interesting and it's going to be useful. And so what we're gonna do on Thursday is talk about a particular choice of a hereditary family of graphs that is extremely important. It's going to give us a Hopf algebra where these formulas live very naturally. Okay. So yeah, so I think that's a good place to stop.